Five coolest bionic robots with artificial intelligence by Festo Robotics. You will be thrilled to know that there is a company that introduces bio-inspired robots every single year. They devote an adequate amount of time and resources to bio-inspired robots that are functional but have limited utility. In today's video, we are going to talk about the company Festo and some of its extraordinary bionic robots. So watch this video till the end. Hello and welcome back to the AI universe. Don't forget to subscribe to our channel and press the bell icon to never miss an update on the new things we bring for you regarding the tech and the trends, but also the vital difference between the haves and the have-nots. That being said, let's begin the video with the company itself. So the company appears to be able to take apart what it learns from developing and building these things and turn it into useful new revenue-generating goods more frequently. Festo, a German automation business, has drawn inspiration from an unlikely source: animals. This company has been creating animal-like robots as part of its Bionic Learning Network since 2006. The goal of mimicking natural efficiency is to assist researchers to come up with more innovative and efficient ways to improve manufacturing. Robotic ants, a robot kangaroo, a jellyfish, a dragonfly, and penguins are among Festo's previous efforts. Let's discuss the 5 of the spectacular bionic robots. Festo utilizes e-motion butterflies to demonstrate how ultra-lightweight flying objects behave collectively. The bionic butterflies represent complicated issues in future manufacturing, such as functional integration, ultra-lightweight construction, and most importantly, real-time optimal network communication between different systems. The e-motion butterflies are a great example of how the virtual and real worlds can coexist. Individual flying items are coordinated independently and safely in three-dimensional space by an external, well-connected guiding and monitoring system. The communication and sensor technology utilized to regulate the butterfly's collision-free collective movement is an indoor GPS. Process stability is ensured by combining integrated electronics and external camera technologies with a host computer. The artificial butterflies are equipped with integrated electronics to precisely mimic the flight behavior of their wild counterparts. To impact the quick flight movements, these regulate the wings precisely and separately. Controlling the e-motion butterflies does not necessitate the use of a human pilot. The host computer stores pre-programmed flight pathways for the bionic butterfly maneuvers. They can, however, fly independently using additional recorded behavior patterns. There is no different connection between the butterflies in this scenario. Now, witness a man-made Bionic Kangaroo. The average kangaroo can cover about 25 to 30 feet every hop as it bounces through the Australian desert. It's a marvel of efficiency. When the kangaroo lands, its tendons stretch to store energy, much like the spring in a pogo stick, allowing it to quickly accelerate without tiring. It's so proficient at hopping that Festo has been quietly constructing a robot that tries to mimic everything a natural kangaroo can accomplish for the past 2 years. The Bionic Kangaroo is significantly smaller and lighter than the genuine one, weighing only 15 pounds, and constructed mostly of foam. However, it moves similarly to a real kangaroo, using elastic tendons that recharge each time the kangaroo lands. It can jump 3 feet ahead at a time, guided by someone wearing a gesture-based wristband. Festo wants to test out new concepts for use in the automated equipment they create for manufacturing assembly lines. Some of the Bionic Kangaroo's capabilities may eventually help industries conserve energy. Moving on to the next, it is the time of a spider. The Moroccan biker spider served as the model for the Bionic Wheelbot. Professor Ingo Reichenberg discovered a spider in the Ergachebi Desert on the edge of the Sahara in 2008, and it now bears his name. Sabrenis Reichenberg is a species of Sabrenis. The Bionic Wheelbot imitates the cyclist spider's movements. The original spider, which can grow up to 2 centimeters in length, is notable for its movement variance rather than its name. It mixes the typical spider walk with a flying and ground duty sequence. Running is twice as quick as hopping and rolling. Ingo Reichenberg has been interested in the technological transfer of spider movement patterns since he first found them. The outcome is the Bionic Wheelbot, which he has further developed as part of the Bionic Learning Network in collaboration with Festo. In roll mode, the Bionic Wheelbot mimics the natural cyclist spider by rolling over its entire body. He always knows where he is and when he needs to push off thanks to the embedded inertial sensor. He is also faster while rolling than when jogging, and he can handle steep inclines of up to 5%. The Bionic Wheelbot is built of 3D printed polyamide, and the battery is a 7.4-volt, 1000 mAh lithium polymer battery. The actuators include 14 self-locking worm drives and a servo motor, and the radio remote control is done through a tablet. Here comes a fish that is totally artificial. The Bionic Fin Wave underwater robot, based on nature's best propulsion system for specific types of movement, is the newest addition to Festo's collection of bionic animals. The undulating fin movements of aquatic species, such as the polyclad, cuttlefish, and Nile perch, were inspirations for the Bionic Fin Wave team. Fin drives are especially well suited to slow, precise motion and produce less turbulence in the water than, say, a traditional screw propulsion motor. Inspection, measurement, and data collecting could all be performed by robots based on the Bionic Fin Wave. This project's findings could be applied to the development of novel technologies for producing soft robotics components. So, want to know about the process or how it works? Cuttlefish and polyclad marine flatworms have longitudinal fins that run from head to tail along their backs, undersides, and sides of their torsos. The animals move through the water by creating a continuous wave with their fins that travel the length of their bodies. The water is forced rearward by this so-called undulation, resulting in a forward drive. The Bionic Fin Wave manipulates itself forwards and backward, as well as above and downwards, by bending its body in the desired direction. The Bionic Fin Wave's distance from the walls and depth in the water is constantly measured by pressure sensor and ultrasonic sensors, preventing collisions with the tube system. The autonomous underwater robot can connect with its controllers through radio and provide data to a tablet, including temperature and pressure sensor readings. The next up is hand? Wait, what? Yes, the Bionic Soft Hand. The Bionic Soft Hand has no bones. Its fingers consist of flexible bellows structures with air chambers. A special 3D textile coat made from both elastic and high-strength threads encases the bellows in the fingers. It is possible to know exactly where the structure develops and creates power, as well as where it is stopped from expanding, thanks to this soft robotics material. This makes it light, flexible, versatile, and responsive, while still having the ability to exert significant forces. Machine learning methods are akin to human learning methods. To classify and learn from their activities, they require positive or negative feedback. This form of reinforcement learning is used by Bionic Soft Hand. Instead of replicating a precise action, the hand is simply given an objective to achieve. It achieves its purpose by trial and error. The Bionic Gripper gradually improves its movements in response to feedback until the task is completed. The Bionic Soft Hand can, for example, rotate a 12-sided cube so that a previously defined side is on top. With the help of a digital twin, built with the data from a depth-sensing camera and computer vision algorithms, the appropriate movement strategy is taught in a virtual environment. Festo's developers have created a compact, digitally controlled valve terminal that is put directly on the Bionic Soft Hand to reduce the effects of tubing. As a result, the tubes that control the gripper fingers do not have to be pulled through the robot arm. As a result, the Bionic Soft Hand may be rapidly and easily connected and operated using only one supply and exhaust tube each. The movements of the fingers can be carefully controlled using proportional piezo valves. At last, we have a bonus for you: a swarm of robotic ants. Festo is expanding its animal robot family. The business has revealed a new robot as part of its Bionic Learning Network, a swarm of ants. The ant robots, known as bionic ants, are inspired by the insect's swarm intelligence as well as its physical body. The robots communicate with one another thanks to a radio module on the ant's abdomen, and piezoceramic bending transducers in the actuators allow the legs and pincers to move quickly and precisely. The ant can see thanks to a 3D stereo camera in its head, and an infrared optical sensor to its underside measures the distance it travels across the floor. Meanwhile, two onboard LiPo batteries supply up to 40 minutes of wireless power before requiring charging via their feelers. Now tell me, aren't you amazed by these awesome multi-purpose robots? Do express your views in the comments. That's it for the day, guys. We hope you have enjoyed the video. Make sure to like the video and subscribe to our channel for such interesting topics. And we'll catch you in the next one. Until then, peace.